Hello everyone, in this video tutorial, we will see how we can do sign language alphabet detection and recognition using YOLO-NAS. We will fine-tune the YOLO-NAS model on the custom sign language letters dataset available on RoboFlow. After training the YOLO-NAS model on the sign language letters dataset, we will test it using random images and videos. We will also test the fine-tuned model on the live webcam feed. And furthermore, we will also export the custom trained model in the ONNX format. So let's get started. So here is our Google Colab notebook file. So in the first step, before running the script, please make sure that you have selected the runtime as GPU. So you can see that my hardware accelerator is set to GPU and GPU type is T4. Okay, so now in the next step, what I will do is in the step number 1, I will install all the required packages. So just run this cell. It will install the super gradients, IMUtils, RoboFlow, and PyTube package. So now you can see that the required packages are getting installed. So this might take a few minutes so to get for these packages to get installed. So after these packages gets installed, we will restart the runtime again, and then we will import all the required libraries. So I am just waiting for these packages to get installed. So we have installed the packages. So now what I will do in the next step is to just go over here and click on restart runtime. Okay, and after restarting the runtime, so now I will import all the required libraries. So just run this and then also run this over here. And so now in this way, just import all the required libraries. So now you can see that all the required libraries are being imported. So this might take few seconds. So it's done now. So now in the next step, what I will do is I will just create a directory by the name checkpoints2. And inside this directory, I have the folder name sign YOLO-NAS run2. So inside this folder, I will save my best model weights, my last epoch model weights, and my average model weights. Plus, I will also save the logs file over here as well. So I will be creating a directory by the name checkpoints2. And inside this directory, I will be creating a folder by the name sign YOLO-NAS run2. And inside this folder, I will save my average model weights, best model weights, and the model weights on the last epoch. So just run this cell now. So now you can see that I have instantiated the trainer over here as well. Okay. So now in the next step, what I will do over here is I will just export the dataset from RoboFlow into the Google Colab notebook. So as in this video tutorial, we are doing sign language letters detection. So here is the dataset. So this is the American Sign Language Letters Computer Vision dataset. So you can see over here, you can see the demo video over here as well. So you can see that here is the overview of the dataset. The American Sign Language Letter dataset is an object detection dataset of each ASL letter with a bounding box. Okay, so what we can expect, one could build a model that reads letters in a sign language. Okay, so what our target is that we will be fine-tuning or training the YOLO-NAS small model on this dataset, and our model should be able to read letters in sign language. So in the what output should we expect, like that the person you can see over here. So in this way, our model should be able to read letters in the sign language. So this is the output we should expect, that our model should be able to read letters in the sign language. So as you can see here, the use case is that one could build a model that reads letter in sign language. So now we are just training or fine tuning the YOLO-NAS model on this American Sign Language letters dataset, and our goal is to build a model or fine tune the model YOLO-NAS model to read letters in sign language. So our goal is that YOLO-NAS model, trained YOLO-NAS model on this dataset should be able to read letters in the sign language. Okay, so now we are just exporting this dataset from this RoboFlow into our Google Colab notebook. So to export this dataset from RoboFlow into the Google Colab notebook, so just click on download this dataset, and from here, just like the 𝗬𝗢𝗟𝗢𝗃𝟴 format, and then click on continue. So if you are just running this this script in Python or Visual Studio or Spider ID, just click on terminal and just copy this from here. If you are just doing on Python, Spider ID or VS Code. But if you are using Anaconda Navigator or Google Colab Notebook or any Jupyter Notebook, you just need to copy this from here and just click over here, just copy this from here and just paste all this over here and just run this cell now. So now we are just downloading this dataset from RoboFlow into our Google Colab Notebook. So if you just see this dataset, we have 720 images in our dataset. Okay. So in the dataset, you can see we have a total number of 720 images in our dataset, out of which 504 images are in the training set, 144 images are in the validation set, and 10% images are in the testing set. So we are using 70% of the images for the training, 20% of the images for the validation set, and in the testing set, we have the 10% of our data set. So it is the normal practice in computer vision to take 70% of the images in the training, 20% of the images in the validation set, and 10% of the images in the testing set. But you can rebalance your data set as well. You can take 80% of the images in the training, 10% in the validation, 10% in the testing set. But usually we take 70% of the images in the training, 20% of the images in the validation, and 10% of the images in that testing set. Okay, so here you can see that here we have all the images. You can see over here, we have the train, validation, test folders, and we have 26 different classes in our data set as English as we have total number of 26 letters in the English language. So we have in this data set as well, we have 26 different classes from A to Z. We have 26 different letters. So we have 26 different classes. And if I just go to the health check, so now you can see that our data set is balanced. So it's not unbalanced. So you can see this green line over here. This shows that our data set is entirely balanced. So in case of unbalanced, you can see the red line. You can see the yellow lines over here. If some class is unbalanced, here we can see the yellow lines. Plus, we can also see an alert like this class is unbalanced. But in this case, our complete data set is balanced, and this is very good. Like we have a balanced data set. Okay. So now you can see that we have total 720 images in the data set, and we have total number of annotations 720. And the median image ratio is 330/36 x 40/48. So now what I'm doing is that now you can see that we have downloaded this data set in our Google Colab Notebook. So now you can see that here we have the data set. Okay, and here we have the train, test, validation folder. We have the images as well, and plus we also have the labels over here as well. Okay, labels represent like where we have the bounding box, the location of the bounding box. Like in the labels file, we have the coordinates of the bounding box saved. Okay, so let me just show you. So if you just see in the label .txt file, in the labels folder, this is the class. This represents what class it is, and these are the x1, xy coordinates, x1, y1 coordinates, or you can see that these are the x2, y2 coordinates. So here are the x1, y1, and these are the x2, y2. So x1, y1 coordinates represent the top left corner, and x2, y2 coordinates represent the bottom right corner. And this is the class which you can see over here. Okay. So now I'm just, you can see that downloaded the dataset in our Google Colab Notebook. And here we have a data.yml file. You can see over here number of classes 26. And here we have the train, test, and validation paths. Okay, and here we have the URL of the dataset here as well. Okay, so now you can see that we will be just loading our dataset parameters into this dictionary. So here I will just pass the data directory folder name. So just copy this from here and just paste this over here. Okay, and here we have the train images for directory path. Here we have the train labels directory path. And here we have the validation images and validation labels. And here we have the test images, test labels directory path. So now you can see that here we have total number of 26 different classes into our dataset. So in the classes, I have written all the name of the classes which we have in the dataset. So these just follow the sequence. So here you can see that in the data.yml, we have the A, B, C, D, E. So I will just write all the classes name into the same sequence as it is written in the data.yml file. So that classes name should be in the same sequence as it is written in the data.yml file, which you can see over here. So just run this cell now. Okay, So now I will just pass the values for the dataset parameters into this dataset parameter argument over here. So I'm just passing these values of dataset parameters, okay, into this dataset parameter argument, which includes a training images directory, test validation image directory, test images directory, and our main directory as well. Okay. So now I will just inspect the dataset defined earlier. Now here I'm just inspecting the dataset I've defined earlier. So now I will just plot a batch of training data with the augmentation applied to it, so to see how our training dataset basically looks like. So just I am just plotting a batch of training data with their augmentations to just see how our training data looks like. So I will be using dot plot function for this. So now you can see that here is a sample images from our training data, which you can see over here. So now I'm just instantiating my model. So you can see over here, we are just using YOLO-NAS small model. So YOLO-NAS comes with 3 different models: YOLO-NAS small, YOLO-NAS medium, YOLO-NAS large. So you can use any of the model, but YOLO-NAS, let me tell you how each of these models are different. YOLO-NAS small is the YOLO-NAS S, or YOLO-NAS small is the smallest among all other YOLO-NAS models. YOLO-NAS small is basically fastest among all other YOLO-NAS models. So YOLO-NAS small is the fastest among other YOLO-NAS models, which include YOLO-NAS medium, YOLO-NAS large, but it is less accurate as compared to other YOLO-NAS models. So YOLO-NAS small model is less accurate as compared to other YOLO-NAS models. While YOLO-NAS large model, which you can see over here, YOLO-NAS large model is the most accurate among other YOLO-NAS models, but it is less fast. So in case of YOLO-NAS model, YOLO-NAS small, we have the fastest model, but it is less accurate. But YOLO-NAS large is the most accurate among YOLO-NAS models, but it is less fast as compared to other YOLO-NAS models. So just run this cell. So now we are just instantiating our the model, and here we have just passed the pre-trained weights as Coco, and here I've just downloaded the pre-trained model weights over here. So now we will define metrics and the training parameters. So now please remember that there are few mandatory arguments that you must define in the training parameters over here. So there are few arguments that you must define in the training parameters, which include the maximum number of epochs. So in the maximum epoch, you just define the number of epochs on which you want to fine tune or train your YOLO-NAS model on any custom data set. So in maximum epochs, we define the number of epochs on which we just want to train or fine-tune our YOLO-NAS model on any custom dataset. In the loss variable, we define the loss function. It can be any PP YOLO-NAS or any other YOLO-NAS function. And in the optimizer, we just define which optimizer we want to use. We can use ADAM optimizer, RMS prop, or any other optimizer as well. And in the training metrics, we just find the metrics to log during training, and in the metrics to watch, we define what would be our evaluation metrics. So it can be mean average precision with IRU 0.5, or it can be mean average precision when IRU varies from 0.5 to 0.95. So these are the few mandatory arguments that you should define or must define in the training parameters, while you can skip the other arguments. But these 6 are the mandatory arguments that you must define the training parameters. So now you can see that in our training parameters, we have defined multiple arguments, not only these 6. So you can just define these 6 arguments, or you can define other arguments as well. So now you can see that we have selected the optimizer as ADAM. We have defined the maximum number of epochs as 25. And here we have defined the loss as PPE YOLO-E loss. And here we have defined the learning mode as cosine and initial learning rate as 5 epsilon minus 4. Okay, and here I have just warm up initial learning rate as 1 epsilon e minus 6 over here. Okay, so just run this cell now. So here I will just download some demo videos from the drive into this Google Colab notebook. So I just placed some demo videos into my drive. So I'm just downloading those demo videos from drive into this Google Colab notebook. So I will be using these demo videos also to evaluate my trained YOLO-NAS model on American Sign Language dataset. So after training the YOLO-NAS small model on American Sign Language dataset, we will be testing our model, like how our models perform on these randoms videos, like whether our model is able to detect the sign to read the letters in the sign language or not. So we will test our model, like whether our model is able to read the letters in the sign language or not. We will be using these two demo videos. Okay. So now I will be starting the training. So let's start the training. So the training will take around 1 hour 30 minutes. So as the training starts, I will just pause the video, and when the training complete, I will be back and then we will discuss the results as well. So the training is about to start. So now you can see that the training has started. Okay, so the training will take around 1 hour 30 minutes. So I'm just going to pause the video, and when the training completes, I will be back and then we can discuss the results. So now you can see that number of GPUs we are using. We have one GPU available on the machine. We have that dataset size of training that images in the dataset is 504. You can see over here as well. Okay, we have 504 images in the training dataset, and you can see over here as well, we have 504 images in our training dataset. We have the batch size as 16, and we have the number of iterations will be 31. So the training has started. So let me just pause the video, and when the training completes, I will be back and then we will discuss the training results. So I have trained the YOLO-NAS model on the sign language dataset. So here are the training results. So now you can see over here, the mean average precision with IRU 0.5 is obtained as 0.8592, which is 85.92%. Plus, if I just go overhead, and here we have the training losses. So you can see that the loss is continuously decreasing. So it is continuously decreasing. Plus here we have the validation result. We have the F1 score, mean average precision, PP, YOLO loss. So if we just see that the F1 score with RU 0.5 is 0.1625, and the mean average precision with RU 0.5 is 0.8512, and the recall with RU 0.5 is 0.9952, and the precision with RU 0.5 is 0.091. And here you can see we have different losses. Okay, so that's good. You can see here we have the training losses, and here we have the validation results. We have the F1 score, mean average precision. We have the PP YOLO E loss. We have the precision and recall values as well. Okay, so after training, as I've already told you, I have created a directory by the name checkpoints2, and inside that directory I have a folder by the name sign YOLO-NAS run2. So inside that folder I have my last epoch model weights by the name saved by the name checkpoint latest.pth, and I also have my best model weights saved by the name checkpoint-best.pth. So on the epoch on which the model gives us the best mean average precision, we have the best weight stored by the name checkpoint-best.pts. So these are the model weights on that specific epoch on which we get the best mean average precision. And here we have the average model.pth, and the checkpoint-latest.pts represent the model weights on the last epoch. So we have trained the YOLO-NAS model on sign language dataset for 25 epochs. So these are the model weight on the 25th epoch. And here we also have the different logs file over here. You can just explore it. We just don't need to review this because we will not be using this further. So, but if you just want to check it, you can check the logs file over here as well. So as I already told you, we always take the best model weights and test our model on random images as well, and random images and videos. So I'm just taking the best model weights. You can see that checkpoint-best.pth present my best model weights. So I will just copy path from here and just paste this path over here. Okay, so I will be using this best model weights to test my model on random images and videos. Plus, if I just go above further, so now you can see over here inside the dataset parameter, I have defined the classes. So as you know that in English we have 26 different letters. So as this is the American Sign Language letters dataset, and in this dataset we have 26 different classes. Okay, so we have in this dataset we have 26 different classes, and each letter in this letter represents a class. So A represent one class, B represent other class, C represent other class, D represent other class. So from A to Z we have 26 different letters, and in this dataset we also have 26 different classes as well. So if I just point the dataset parameters classes length, so it will come out to be 26. So if I just go below further, just go to the point. So here you can see that if I just find the length of my dataset parameter classes, so it will be 26. And here so we have just trained the YOLO-NAS small model on the sign language dataset. So here I'm just passing the pre-trained model YOLO-NAS small. So you can use YOLO-NAS comes with 3 different models: YOLO-NAS small, YOLO-NAS medium, YOLO-NAS large. So you can use either YOLO-NAS small, YOLO-NAS medium, YOLO-NAS large. It's all your choice. So YOLO-NAS small model is the fastest among other YOLO-NAS model, but it is less accurate. While YOLO-NAS large is the most accurate among other YOLO-NAS model, but it is less fast as compared to the other YOLO-NAS models. So just run this cell now. Okay. Okay. So you can see over here, successfully loaded model weights from checkpoint 2. So now we'll evaluate the best trained model on the test dataset images. So if I just go to the dataset, here is my test dataset images. So now we will be evaluating our model on this test dataset images. So just run this cell and see what mean average precision, recall, F1 score we get on the test dataset images. So you can see over here the mean average precision with IOU 0.5 is obtained as 0.8915, which is 89.15%. This is good. And the F1 score with IOU 0.5 is obtained as 0.1779, and the recall score with IOU 0.5 is obtained as 1, and the precision value with IOU 0.5 is obtained as 0.1019. And here we have different losses as well, IOU, DF1 and other loss here as well. Okay, so now from the validation dataset, I will just take a sample image by just copying path from here. So just click over here, copy path, and just add this path over here. Okay, and just so now we are just using the best model weights. We are just testing our model on a validation dataset image, and we will see whether our best model is able to detect the sign language or not. Okay, so now you can see over here, this is a U sign in the sign language terms. So our model has successfully detected that this is a U sign. So you can see here it is U, and here we have the confidence score of 0.51. Like the model is 51% confidence that this sign represent the U alphabet, U or U letter. So this sign represents the U letter. Our model is 51% confidence, and our model is correctly confident because this sign represents the U letter. Okay. Okay. So we are just saying that our model is correctly confident, and this sign actually represents the U letter. Okay. So now we will further go ahead and just test our model on 2 demo videos. So I've already downloaded the demo videos before training. So now I will just test our model on this 2 demo videos. So we are just importing torch. So in this case, if we don't have the GPU available, I will be using CPU. But Google Colab offers free GPU, so it's always better to utilize this free GPU. So now I will be doing prediction on this sample input video. Okay. So this might take few seconds, and let's see how it goes. So now we are just detecting the different hand signs on this video, and we will see whether our model is correctly able to find that hand sign or not. Okay, so I have already done this video and it was detecting the hand signs correctly, but I will just show you again. So let's see whether our model or trained model on the sign language dataset after training, is it able to detect the hand signs correctly or not. Okay, so this might take few seconds. So let's wait and see. As it completes, then I will show you the output video on the big screen as well. So now you can see that it's complete. Okay, so let me just download this video and just navigate my screen towards this output video. So now you can see over here, let's start it. Okay, so now you can see over here, this is the G sign. Our model has correctly detected that this is the G sign. So that's good. This is the H sign, and you can see that model is correctly identifying that this is the H sign. And this is the I sign, and our model is correctly identifying that this is the I sign. So that's great. So we are able to track 3 signs successfully over here. So our model was correctly able to classify those signs, and what this sign represents, if it represents a G or I or U letter or so. So now I will test on the demo video too. So now you can see that I have already downloaded the demo video too. I've already shown you that before training, we have downloaded 2 demo videos. So we have tested on the first demo video. So now we will test on the demo video too. So just pass the input video path and output video path. So our output will be saved by the name detections.mp4. So this is the input video path. So now you can see here, just copy path from here and just add this path over here. You can see that just paste this path over here, and in the output video path, you just write the name of the by which you want to save your output video. So I just want to save my output detection video by the name detections.2.mp4. Just write the name over here by which you want to save your output video, and just do the detection on this video. So now you can see that we are just detecting different signs or use on this video, and let's see what results do we get. Okay, so now we are just predicting different signs over here. Okay, so this might take few seconds more, and let's see. So the processing on this video is done, and let's display the output video over here and see whether our model is able to detect different hand signs correctly or not. Okay, so just run this. So as you see that our output video is saved by the name detections2.mp4. Just copy path from here and just paste this path over here. And I've already added this path, but if you just want to know how does it work, so you can just add this path over here, and here you can see the output video. So this might take few more seconds until we have the output video over here. Okay, so just waiting for the output video to display over here. So now you can see here we have the output video. So the screen size is small. So let me just download this video and show you how our output looks like. So I'm just navigating my screen towards the output video. So now you can see over here, let me play it from the start. We are able to detect the W sign. So this is the correct detection. We are also able to detect the X sign. This is also the correct detection. We are also able to detect the Y sign. So this is also the correct detection. Okay. So we are also able to detect the Z letter. So this is also the correct detection. Okay. So now you can see over here, our model is able to detect the different sign language letters very correctly. So now in the next part of the video, I will just download this best model weights from here. Okay. And we will be testing on it on the live webcam and see whether we are able to detect different hand signs or not. Okay. So let's go toward the next part. So now I will test my trained model or American Sign Language Letter Detection model on the live webcam feed. So you can see that I have created a folder YOLO-NAS Sign Language Webcam over here. So I have created an empty folder over here. So in the next step, I will just open PyCharm. So now I am opening the PyCharm. And after opening PyCharm and I will create a new project over there. So let me just create a new project over here. So I will go to File and just create a new project over here. So I will just click on File. Okay, and click on New Project from here. And then I will select my new project folder from here. Okay. Then I will just go to F. In my F directory, I have created a folder by the name YOLO. What is the name of this folder? YOLO Sign Language Webcam. So this is the name of the folder. Okay, so I will just search for this folder. So here you can see that here we have the folder YOLO-NAS Sign Language Webcam. So I will just select this folder and click on OK. So now you can see over here, this path matches over here as well. And I have selected the base interpreter as Python 3.10. Okay. Then I will click on create a new project and then select this window from here. Okay, so now you can see that it's creating a virtual environment. So this might take few seconds to create a new project, and it's updating the interpreter paths as well. So now we can see that we have created a new project over here. So now to run our trained YOLO-NAS model on the to test our trained YOLO-NAS model on, as we have trained or fine-tuned our YOLO-NAS model on the American Sign Language Letters dataset. So I will just first of all install all the required libraries or the packages. So basically to run our YOLO-NAS trained model on the Python script, we require two packages. One is OpenCV and other is SuperGradient. So one way is to install those packages, to go to File and then click on Settings from here. And then I will just go to the project and then Python interpreter. And then if I just click over here, plus, okay. Okay, so now I will just write here the name of the package, OpenCV-Python. And if I just click over here and install package. But if you have tens of packages to install, so this is not an ideal way to just write each of the package name over here and install it one by one. Okay, so I will just close this and choose another way. Okay, so I will just create a requirements.txt file over here. So it's requirements.txt file over here. And in the requirements.txt file, I will list all the required libraries which I require. So I will require OpenCV-Python library, and other library which I require is SuperGradients. So super-gradients, and the version of this library is 3.1.0. Okay, so I have listed all the two packages or libraries which I just want. So now you can see that OpenCV package is already installed successfully. To install the SuperGradients package, because we have installed the OpenCV Python package by going into the settings. I have shown you the way you can install the packages. So by going to the settings and just go to the interpreter. So to install the packages by just writing into the requirements.txt, you will just open the terminal over here, and let me just make it work. Let's wait for a few seconds. Okay, it's working. So I will just write pip install -r requirements.txt. Okay, so it will install. So OpenCV Python package is already installed. So this will appear our requirements already satisfied. Okay, what error we are getting is no matching distribution found for SuperGradient. So it's SuperGradients. Okay, so I have just misspelled it. So just change it to now run it again. And let's install this package SuperGradients. Okay, so this might take few seconds to work. Okay, so now you can see requirements already satisfied because OpenCV Python package is already installed, and therefore disappearing requirements already satisfied, while SuperGradients package might take some time. Okay, I think I have already, I have already installed the SuperGradients package, so its appearing requirements already satisfied. But if you have not installed it previously, then this will take around 5 to 10 minutes for both of these packages to get installed. So after installing these packages, I will just create a directory by the name model weights. In this directory, I will place my best model weights file. Okay, so now if I just go over here, so now you can see that here I have the model weights directory. So I will just go to downloads and just copy these weights from here and just paste this weights file over here. So now you can see that we have pasted the weights file. So now let me just create a .py file and just write out the code and test it on a script. So sign language webcam.py. So this is the name of our .py file. So in the first step, I will import all the required libraries over here. Okay, so I will just write import cv2 over here. And next, I will just import some packages from the SuperGradients or some functions from the SuperGradients package. I will write from super, okay, from super dash gradients. Why it's not giving me auto suggest option over here? From super gradients import, okay, dot training import models, import models, okay, and then write from super dash gradients import dot common dot object dash names import models. So it's looked fine till now. Then I will write model is equal to models dot get. And here basically we have fine-tuned the YOLO-NAS small model or American Sign Language Letters dataset. So I will just write basically I have fine-tuned the YOLO-NAS small model or American Sign Language dataset. And number of classes in our dataset are 26. And I will just define the checkpoints path over here. So we have saved our model weights over here. So I will just add this path, model dash weights, ckpt dash west.pth. Okay, so it's all working look fine now till now. Next, what I will do is model. I will write output is equal to model dot predict dash webcam. Okay, so let's test this on a live webcam and see what results do we get. So now I will write in the terminal Python sign language dash webcam dot py and let's run it. Okay, I think the file name is not correct. Let me just correct this out. Okay, it's webm. Okay, so now just run it again. Okay, so now it started to execute, and let's see whether I will just raise my hands towards the camera and see whether it is able, our trained model is able to track the hand signs or not. Okay, hand letter signs or not. So now you can see that the letter and open up my hand first of that of you. And that share with my I was just trying to check if the speech shape or not. But like it was not detecting the C shape, but it has detected that this is the S sign. Let's see whether it is able to detect the V or K sign. It's W or K, and whether it is okay. So our model works fine in the real time as well. Okay, so the results look very good. So let's export our model into the ONNX format and see how does it goes. So let me just pause this. To export the model into the ONNX format, I will just comment this out and just write over here models convert -2 -ONNX as we are trying to convert our model into the ONNX format. So if why we want to convert our own model to the ONNX format, for example, if you just want to deploy this model into the Android device, so first we will convert our model into the ONNX format and then we convert model into any other format. For example, to deploy this model into the Android device, you need to convert this model into the TF-Lite format. So first of all, I will convert this model into the ONNX format and then you can convert this model into the TF-Lite format to deploy this on the Android device. So here I will just write model is equal to model, because here you can see that we have the saved it by the variable name model. So I'm just writing this over here as well. And our input shape we define over here. Input shape is equal to 3,640,640. And out dash path will be like we just write the file name. Okay, so I just want to save this model into custom.ONNX. So this will be my ONNX file name. So okay, so just run this now and see whether it works fine or if there is any issue. So now we are just converting our model into the ONNX format, and let's see whether we are able to convert our model into the ONNX format or not. So if there is any issue, we will definitely fix it out. So this might take few seconds before we are able to convert our model into the ONNX format. Okay, so I hope it will be converted into ONNX format, but if there any issue appears, we will fix it out, definitely. So this might take few more seconds. So currently there is a warning, input shape is depreciated, but this is okay, but this is not a sign to worry about much. Okay, so now it might take few more seconds. Okay, so let's wait and see how does it goes. So I'm just waiting for it to complete and convert my model into the ONNX format and just refreshing it. Currently it's not converted. Okay, we can ignore this. I think the model is converted into the ONNX. Let me go to the folder. And so now you can see over here, we have converted our model into the ONNX format, and here you can see the custom.ONNX file. So why we need to convert our model into the ONNX format? For example, if you just want to deploy this model into an Android device. So first of all, you just convert your model into the ONNX format, then you convert your model from ONNX to the TF-Lite format to deploy into the Android device. So first convert your model into the ONNX and then convert into from ONNX to TF-Lite to deploy into the Android device. So that's all from this video tutorial. I hope you have learned something from this video tutorial. See you all in the next video tutorial. Till then, bye-bye.